Okay. Today we're going to talk about degree and radian measurements. Nothing real difficult today, but there is some new information. 1 degree is 1/360th of the circle. So 1/360th of a rotation. So I could try to draw a, that's more than 1 degree. That's probably like 5 or something. But the idea is that it's just a sliver, right? And we use that little symbol to say that it's in degrees. Okay? Here's that symbol. Well, we want to talk also about radian measurements. So far you guys have converted from degrees to radians, and some of you guys have come up with a formula. We're going to formally introduce that today. But the question is, what is a radian? If we think of a degree as 1/360th, we said there's 360 of them in the entire circle, then how many radians are there? And here's how we really define a radian, okay? We say that a circle has a radius. Okay? And when we wrap that radius around the circle once, that will form an angle measure of 1 radian. So let me try to explain better what that looks like. This arc that's in red, is that more than 1 radius or less than 1 radius? It's less than 1 radius. This red mark, is that more than 1 radius or less than 1 radius? So raise your hand if you think you can tell me where approximately 1 radius would end up. This would be less than 1 radius because it's just that much, whereas the radius is this much. If I wrap it like this, that's much more than 1 radius because that length compared to, that's a lot more. So we'll see who wants to tell me. I need a volunteer. Thank you, Hannah. Hannah, you tell me when to stop when you think I've wrapped 1 radius around, okay? Okay, so. Well, first of all, Hannah, I will not chastise you because in this class of leaders, you're the only one to raise your hand. So thank you for having the guts to raise your hand and try. So I will talk to you, young lady. You think you went too far? Yeah, if I was a bug and I was going to walk along a line and I was a lazy bug, I would much rather walk along the blue line than the red line, right? So you tell me when the bug would have a hard time choosing which one to walk across, all right? We'll try that again. Okay, yeah, I think that's reasonable. I would say I maybe went just a little bit too far, but I think you've made a very reasonable estimate. Give her a round of applause. All right, very good. So the question from Garrett is, what is the advantage of using radians compared to degrees? There's many advantages. I would say in applications in construction and geometry, you're most likely to use degrees. But that's simply because you have always used degrees. Would you rather work in Fahrenheit or Celsius? Well, of course, you're very comfortable with Fahrenheit. But there are times where Celsius lends itself better. Radians, without a doubt, lends itself better when we're working with abstract mathematics. And we will show you some applications of formulas where radians work better. So, if I told you how many degrees are there in a circle? 360. How many radians are there in a circle? You say 8, you say 6, 8, infinite. 360 of them in one circle. How many of these pieces, how many, you say 8 still, okay. 7.2. Okay, one person got it third hour and one person got it this hour. So 2 pi. 6.28 of them. That's what we did past couple days, right? Watch, watch. Okay. That's another radian. A radian is about 57 degrees. And that's another one. So I have a little bit more than 3 radians that fit in the 180 degrees, right? In fact, I have exactly 3.14 that fit in 180 degrees. Oh. No, this mark right here is not pi. This is 3. This mark here is pi. Okay? So you're right, Miss Anna, to think about that. This is 3. That's pi, 3.14. So we're short by a sliver. Okay? So then as I kind of carry on my way and I try to draw this accurately, there's another one. There's another one. There's another one. So I've got 6 of them, and I'm left over with, so this is 6 radians right here, and I'm left over with 0.28 more. So some people don't like it because they're like, well, there's not a whole number of radians that fit within a circle, whereas 360 there is. We didn't pick it because it was a nice number. We picked it because it works very well in mathematics, and you're going to see some of the applications that make things easier as we move forward. So what you want to be able to do then is you want to be able to convert between degrees and radians. I think these 2 gentlemen picked up a formula that they wrote down, and it's 100% correct. If I want to convert from degrees to radians, well, hi there, friend. Okay, now you don't know me. Okay, I'm awkward. Okay. So, if we have an angle measure and we use this as our angle measure, okay? This is, anybody know what this sign is, the symbol is? Theta. Who said that? Thank you. Where'd you learn about that? Good for you. All right. So this is theta. Theta is like an oval or an egg with a line through. It's spelled, well, in Greek, it's spelled like this. In English, we would spell it like this. Okay. Whoop. Need a T in there. And it's the Greek letter that makes the sound TH. So Greeks didn't put a T and an H together. They had one letter, theta, and it made the th sound, okay? So that is generally the variable that gets used to use angle measure. If you don't like the Greek letters, then you might want to try a different class. We're going to use a lot of them in mathematics as we move forward. Delta, epsilon, alpha, beta, the whole way through. So theta is what we use. And as we want to go from degrees to radians, theta times, okay? And we're going to convert to radians. So radians have a pi in it, correct? So we're going to say pi, and then pi radians is how many degrees? (180). So if you take theta and multiply it by pi over 180, that's your conversion. If you want to move, yes. It could be x. It's just like x or y, or generally it's always used to refer to angle measure. Yep. So if you want to go the other way, you take theta and you multiply it by 180 over pi. So we can do all of these conversions. I'll show you how one of them works, and then we'll play a little bit of a game. So I know you guys got into it yesterday. So let's go down here and rewrite each angle in radian measures a multiple of pi. So 0 degrees is how many radians? Thank you. So 30 degrees is how many radians? Pi over 6 radians. 45 is 60 degrees. 90. Pi over 2. So how about 360? 2 pi, 240. What divides evenly into 240? How many times 60 go in? 4 times, so it's 4 pi over 3. So that's the conversion process that I generally use. That goes rather quickly. However, if you're given 105 degrees, you don't see another one that goes in real easily. So you're going to use your conversion. You'll take your degree measure, which is 105, and you'll multiply it by pi divided by 180. So 105 pi over 180 is going to be your fraction. Some people don't know how to reduce that fraction. What divides evenly? Well, you can go to your calculator, and you got this great button, 105. If you hit, 105 divided by 180. And if you just simply hit math and enter on convert to fraction, it will bring it to 7/12. Okay. Otherwise, you can, obviously they both divide by 5. They both divide by 3. They actually both divide by 15. So this ends up being 7 pi over 12. Okay. You must write it in reduced form. Now I'll just show you one more little trick. Okay. If 30 is pi over 6, what would 15 degrees be? Pi over 12. And I know that 15 goes into 105 7 times. So now I've got another one I can use, 7 pi over 12. So, all sorts of ways like that. So we'll be able to convert back and forth now between degrees and radians using our formula. Okay. So what I have above here is, another unit circle basically where you can write 2 pi over 3 and 120 degrees and all that stuff, okay? And so I'm going to give you a little bit of time to fill that in on your own to see what you remember. But before I do that, we're going to challenge each other to another game, okay? So you had so much fun yesterday, and remember, only boring people get bored. So as soon as you roll your eyes at me, remember, you're classifying yourself in a certain category. So go ahead. I'm going to give you 1 minute to review the conversions. I would look at your front pages, and you're going to challenge your partner. Ready, set, go. Go both directions. If I say 45, you should say pi over 4. If I say pi over 4, you should say 45. Zero degrees, 0, 30 degrees, pi over 6. I'm giving you 1 minute. Fill in as much of it as you can. Go. Okay, you can finish that off whenever. We're going to move on, get to other stuff, so you guys have some time to work. Okay. Here we go. Flip it over. I used to cover this. Megan was seeing this a little bit last year probably. And that's converting between degree decimals and degree minute seconds. We're not going to do it because we just don't see it that much moving forward. I'm just simply going to tell you how it's used. If I try to draw 1 degree, maybe 1 degree. Okay. Obviously, you can see that 1 degree, it looks pretty small right there, right? But as you travel further and further on, it gets wider, doesn't it? And so you might like to talk about a half a degree or a fourth of a degree. What they do to break them up is they talk about degrees, minutes, seconds. So you could talk about a number between 36 degrees. Whoop, don't do that. 36 degrees and 37 degrees. You would have a number, say 36 degrees, 12 minutes, and 52 seconds. And that's how we kind of come to a more precise measurement of a degree. There's also a decimal representation that maybe it's like 36.1543. I don't know what it is, but we would learn how to convert back and forth. Why would you use that? When I was a land surveyor and I was plotting out different points of land and buildings, you want to get it just exact. Well, you can see how quickly 1 degree can really become larger and larger over space. We would go to the nearest 5 seconds when we were doing measurements. Over the course of 300 feet, 5 seconds would be about an eighth of an inch. So we could be confident that that space would only be about as big as an eighth of an inch over 300 feet. So that's kind of the application. We're just going to skip it, okay? Not going to do it. Cross it off. Sketch an angle in standard position. You should be able to know how to sketch an angle and what that looks like. I don't even think there's any like these in your homework, but you'll apply it tomorrow. 42 degrees. Anytime you sketch an angle, you'll say, do we have to do it? Yeah, you do. You have to do it like I'm doing it right now. 42 degrees, which quadrant? And an angle has two sides. It has an initial side and it has a terminal side. The initial side of the angle always goes on the right side of the x-axis. The terminal side will end up in whatever quadrant you want. Now, when you draw that angle, you always show the direction that you rotated. Okay? So you just draw a little arrow to show your rotation. So that's approximately a 42-degree angle. We don't have to be perfect. Just get the right general vicinity and we'll call it good. What's different? What? You don't have to draw the circle. Negative 113, which quadrant? Third. You're going to go backwards. There you go back 90 and a little bit more. So, that'll be negative 113 degrees. You draw your arrow to show your rotation. The first two were degrees. How did I know they were degrees? Because of the symbol. The next one, degree or radians. How about the fourth one, the degree or radians? Which is it? Radians, because it does not have a degree symbol. So, some people may say a radian has to have a pi in it. No, it doesn't. Okay? It doesn't have to have pi. We did some examples like yesterday. 4 pi over 3, how many degrees is that? 240. So sometimes you convert it so you can then draw it. Easy peasy. What do you think? Yeah? Negative 4.6 radians. So this is where you kind of need to have in your brain that this is negative 3.14. This is negative 6.28. Negative 1.57. Negative 4.71. So there's decimal representations for all these spots as well. Okay? Because if you take pi divided by 2, you get 1.57. So if I go negative 4.6, which quadrant? Second quadrant. And you can see you're going to be a little bit short of the other spots. There you go. And sometimes you go around more than once. 420 degrees is obviously around more than once, isn't it? So what I'm going to do is draw my initial side. And I go, how many degrees more than once do I go around? 60 more. So I'm going to go around once and 60 more. And that will be the location. So I have to draw my arrows to show I went around more than once. Otherwise, for all you know, it's just a 60-degree turn. 60 and 420 are what we call coterminal angles. And we're going to talk about those tomorrow, but they end up in the same spot. They have the same rotation. Everybody clear? Questions? Easy? All right, let's get to some of the applications. So, it's your assignment if you want to write it down. I've got a couple examples to do. We don't have many more notes left. It's basically 2 problems or so. Do you remember from geometry the terms arc length and area of a sector? if you have a circle and you draw a sector, that sector, listen to this language, that sector subtends, that angle subtends an arc. It subtends this arc, meaning it basically forms or shapes that section. We call the arc length S. We call the area of the sector K. I'm not entirely sure why they chose S and K, but they did. When you were in geometry, here is the formula that you learned. You would take S, and it would equal, oh my gosh, hold on. The formula that you learned was S was equal to, if we're going to do arc length, that's a portion of the circumference. What's the formula for circumference? 2 pi r. And the portion you're referring to is theta in degrees. So instead of theta, I'm going to write DEG for degrees divided by 360. That's the fraction of the circle that you're talking about. Whatever the degree measure is, you're going to divide that by 360. Do you remember that formula? So watch this now. I'm just going to kind of move things around a little bit because multiplication is commutative, right? I can move things around. And I'm going to come up with a new formula, a much better formula. First of all, what's 2 over 360? Yeah, so I'm going to put degrees here times my pi, and you said divide by 180 times r. You could. It's the same either way, whether it's in front or on top. It's the same thing. So look at it, okay? You see that these expressions are the same? I have my pi, I have my r. 2 over 360 is, 1 over 180. Does that look familiar? That's how you convert from. Okay. All right. Degrees times theta divided by 180. Didn't we just do that? The other side? If you take the degree measure, you multiply by pi over 180, what do you get? You get a radian. So look at my formula now. I could get rid of this bulky formula that I have here, and I could get a nice, easy formula. I have S is equal to R times, this will give me theta, where theta is in degrees. So this is my new formula. Super easy compared to the other one, isn't it? That's part of the reason we really like Radiance is because it makes a lot of things in mathematics work out nicer, okay? We'll do an example here, and then you'll see it, okay? Area of a sector, okay? I won't do the entire conversion because we're running out of time, but K is equal to, you do the same type of thing. You get 1/2 times R squared times theta, where theta is in degrees. I'm sorry. You guys, I'm sorry. Theta is in radians. That's the whole point. We want to be working in radians. If you get degrees, you got to use the top formula. If you have radians, use the other formulas. They're much easier to work with. They're much easier to work with. Sure. We'll do some examples and you'll figure it out right here. Easy formulas. It says find the angle in radians that satisfies the conditions below. We'll use our formula. S is arc length equals R times theta, given theta is in radians. We want to find the angle, so we're trying to solve for theta, okay? Do you know S? What is it? 3 equals, do we know R? Do you know theta? S is arc length. divide by, and you get 3 over 7 is equal to theta. Is that radians or degrees? That's radians. So a radian measurement of 3/7. No, 3 pi over 7 would be 3 times 3.14 divided by 7. That'll be much more. This is just 3/7. Yes. Okay, so, Fran, if you remember this right here, this mark right here, this is 1 radian. So 3/7 would be about like that. Be about that much, okay? Look at the next one. I've changed the problem just slightly. It says radius of 4 and theta is 2 pi over 3. We want to find the arc length. Okay? So radius of 4 and theta is 2 pi over 3. Let's find the arc length. So I set up my formula. S is equal to r theta. Do we know S? Nope, we're finding that out. Do we know the radius? 4. Do we know theta? 2 pi over 3. What's 4 times 2 pi over 3? That's the arc length. A much simpler formula to use than the previous one, isn't it? Okay. Flip it over real quick to the other side. We're just going to do example 5, and we'll call it quits. We're going to find the arc length, and we're going to find the area on of an arc on a circle or a sector of radius 24 that subtends a central angle of 60. So all that means is we have a circle with a radius of 24, and the angle is 60 degrees. Now, do we want to use degrees or do we want to use radians? So instead of 60 degrees, I should use pi over 3. This will make our formula a lot easier to do, okay? So, formula says S is equal to r theta. That will give me the arc length. S is, what is r? What's theta? Multiply and you get 8 pi. If you do area, 1/2 r squared theta. Let's just take a second. 1/2 times what's r squared? 24 squared? 576 times pi over 3. 1/2 of 576 is 288. Divided by 3 is 96 pi. So you can see that it makes things easier. I have a short assignment for you. Just these problems right here. Tomorrow will be a worksheet in class. We'll do most of it together. No, tomorrow's worksheet is generally pretty easy. One concept. I think the stuff that you see on Monday and Tuesday you'll probably feel is a little bit more challenging, but